Okay, so we're on upper triangular matrices. So let's take a look at number 2, actually, first. So pause the video, read it now, maybe answer it. Okay, so if you make the matrix of a linear operator, right, T is sending V to V, and then you choose a basis of V, okay, then what is the kth column of the matrix of T? Well, you look at T on the kth basis vector. That's now a new vector. You can write it in terms of the basis using some coefficients, a1, v1 plus dot 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 plus an, vn. And the kth column of that matrix should just be the numbers a1, a2 up to an. That goes in the kth column of M of T. Similarly, the first column is the numbers c1, v1 plus blah, 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 cn, vn, where you write this vector tv1. Whatever that vector is, you can write it in terms of a basis, and then you put those numbers in the first column. Okay. So now look at number 1. Pause the video, see if you can figure out these entries. Okay, so we know that the kth column should contain a 1k, a 2k, all the way down to a nk. And so those are just the coefficients. You take t, vk, and you write it as a 1k, v1, plus a 2k, v2, plus dot, 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 all the way up to a n, k, vn. And then you put them into the kth column of a matrix. And so those are just what those numbers are. Okay. So I guess aij is when you write t of vj, and you write it in terms of the basis v1, v2, it's the ith coefficient. So it's whatever number ci goes in front of vi. And instead of calling it ci, we call it aij because it came from tvj, and it's the coefficient of vi. Okay, take a look at number 3. Maybe pause the video and solve it yourself. Why is there always a basis so that M of T has its first column full of zeros except one entry, and that one entry will be the first entry? Well, because, and this is actually false, so we need that V is a complex vector space, that the field for our vector space is the complex numbers. Then this is true. If it's the real numbers, it's false. So why is it true? Because over the complex numbers, every operator has an eigenvalue and an associated eigenvector. That's non-zero vector. So there exists a lambda in C. There exists a lambda in C with TV equals lambda V for some non-zero vector V. So then just extend to a basis with V2, V3, Vn of the whole space. This is independent because it's non-zero. It's an eigenvector, and then it's sort of like our V1, but I guess I called it V. And so we create a basis, and then we write M of T in this basis. Then if the first column, what we do is we take the first basis vector, and we write it in terms of all the basis vectors. But the first basis vector is just lambda times the first basis vector. So all the other coefficients are 0. We need lambda of V plus 0 of V2 plus 0 of V3, etc. And you put those into a column, and you get that. Now the rest of the matrix we have no idea, so we just put stars everywhere because we don't really know what the rest of the matrix looks like. So we can just put stars everywhere, and that answers number 6. Star represents some entry of a matrix or vector that we don't care about. It could be non-zero in particular. We don't know that it's 0 or not. What is the diagonal of a matrix? You should just look that up. It's all the entries A, I. Okay, so it's that. That's the diagonal, not that. Okay. And when is a matrix called upper triangular? When all the entries down here are 0, and the non-zero entries are up here. Okay, so an explicit example of a 4 by 4 upper triangular would be 1, 2, 3, 4, 5, 6, 7, 8, and pi, and 17. And so this would be a 4 by 4 matrix. Now I didn't write all the other entries because they are 0. So here's the upper triangular matrix. All right, take a look at number 7 and try it yourself. Pause the video. At least pause the video to read it. Okay, so the matrix of a linear operator in some basis, v1, v2 up to vn of the space, is upper triangular, 1. That happens if and only if, 2, the span of v1 through vk is invariant, is an invariant subspace under T for every k equals 1, 2, 3, up to n. Okay, so we actually have a whole, we call it a flag of invariant subspaces for T. When T has a basis that makes its matrix upper triangular, then we have a whole flag, a one-dimensional subspace that goes back to itself, and then we also have a two-dimensional subspace that goes back to itself, and then a three-dimensional subspace that goes back to itself, and then a four-dimensional subspace that goes back to itself. This is a four-dimensional subspace. That's my picture of it. And that's true. We have a subspace that goes back to itself for every dimension, all the way up from 1 to the full dimension of the space. That happens if and only if a third characterization is that T of vk is in the span of v1, v2, up to vk. It's, these are all equivalent, so that sometimes they're just psychologically easier to handle the third one than it is to psychologically handle the second, than it is to psychologically handle the first. So they're just different ways of saying the exact same thing. And what you should try to do is pick one of them, say the third, and try to prove that it implies the first. Okay, see if you can prove that. And then maybe you should see that try to prove that the third implies the second. Then you should try to prove that the second implies the third. Just try all the different directions, okay, so that you really understand why these are all equivalent. Okay. Should I do one of them? Okay, let's do one of them. Let's prove that 1 implies 3. So we're assuming that the matrix is upper triangular, and we want to show that tvk is in the span of the previous vectors and vk itself. In particular, you don't need vk plus 1, you don't need vk plus 2, all the way up you don't need vn. Okay, so that has to be true. Oh, and this should be for every k equals 1, 2, up to n. Okay, so that's what we need to prove. We're allowed to assume that the matrix is upper triangular. So we need to prove this for every k. So let k be chosen one of the integers from 1 to n, be fixed. And then we'll do a proof, and because we chose k arbitrarily, it proves it for every k. Okay. T of vk is equal to, well, tvk is some vector in the space, so it's equal to some linear combination of the basis, all the way up to and including the kth, and then also the k plus first, and all the way out to the nth basis vector. Okay. But since we're assuming the matrix is upper triangular, what does that mean? Well, these numbers go in the kth column. And if it's upper triangular, then all these numbers are 0. All these numbers have 0 coefficients. Okay? But that just means, so that's from, because the matrix is upper triangular, we know these are all 0. And so that means that this is tvk. But then tvk is just a linear combination of v1 through vk. That means that tvk is in the span of v1 up to vk. We don't need vk plus 1. We don't need vk plus 2. We don't need vn. End of proof. So those 1 implies 3. You should try the other ones. Maybe pause the video and do it. Check your answer in the book. Okay, let's do this one, number 8. Read this now. Pause the video and read it. Okay, so this 0 is the 0 operator. It is the 0 in L of V. 0 in L of V, okay? And what is this thing right here? So this you should think of as P of t, where P is a polynomial that factors into linear factors, right? So if P of x equals x minus 2 times x minus 3, it factors into 2 linear factors, okay? And even if you have another x minus 3, now it factors into 3 linear factors, and we're sort of repeating 3. And then if we did P of t, then that becomes the operator t minus 2, which we think of as t minus 2i, t minus 3, which we think of as 3i, and t minus 3 again. Okay, and what we're saying is that if T has an upper triangular matrix with the diagonal entries lambda 1 through lambda n, so these are actual numbers like 2 and 3, then this is the 0 operator. So how do we check if this thing is the 0 operator? Well, we have to check, okay, so first let P of t equal t minus lambda 1i all the way to t minus lambda n I. We need show that P of t v equals 0 for all v and v. That's how you show that something is the 0 operator. You show that whenever it eats a vector, it gives you 0. Okay, so let v equal c1 v1. So choose a basis and express. Actually, don't just choose any basis. Choose the basis where T has an upper triangular matrix. Choose that matrix. Then P of t v equals 0 if P of t vk equals 0 for all k. So what we're going to do here is we're going to just show that an easier problem that P of t eating the kth basis vector is 0. This we're going to prove. We're going to prove that. Once we prove that for all k, then clearly by linearity this thing is 0 on everything, because it would just come through and it would just hit, it would be P of t would hit c1 v1, the c1 would pull out, and P of 2 would hit v1, but we'd show that's 0, so we get 0. Then P of t would hit c2 v2, the c2 would pull out, and then we'd show that P of t v2 is 0. So this whole thing would then be 0. So all we need to do is, so enough to show P of t vk equals 0 for all k. Okay. So, and P of t is this thing. Okay, so let's try v1 first. So P of t v1 equals 0, since we can put this factor first. We can rearrange the factors because we can rearrange factors in polynomials. You can multiply in any order for polynomials, and we showed that the same thing happens when you plug in the operator earlier in chapter 5a, maybe? Or no, maybe even chapter 4. I can't remember where we did that. Since, P of t applied to v1 equals 0 by putting t minus lambda 1i first. Why is that true? Because t minus lambda 1i on v1, and then we could do t minus lambda 2i, we would just put all the other factors lambda ni after, and they're just waiting, but we'll put this one first. And if we do this one, we're going to get tv1 minus lambda 1 v1. But v1 is an eigenvector because the matrix is upper triangular with diagonal entry lambda 1. So when we do t of v1, we just get lambda 1 v1. And that is clearly 0. And then when you apply the rest of these things to 0, you still get 0. Okay. Now, v2 is a little trickier. So let's do p of t on v2. And this time what we're going to do is put t minus lambda 2. I'm going to stop writing the i's. v2 first, and then we're going to do lambda 1 after that, and then we'll do all the rest. And these won't matter because we're already going to get 0 here. Now why? Well, here we're going to get tv2 minus lambda 2v2. And this tv2 is not lambda 2v2, so be careful. It's a little bit more complicated. tv2 is some number a1v1 plus lambda 2v2, because the matrix of the linear operator looks like this in the second column. Right, we have possibly a non-zero entry there. It's just in the span of v1, v2, so we could have something there. And then we'll do lambda 2, v2. And these will cancel, but this one might not cancel, right? This might not be 0. But luckily, it's just a scalar multiple of v1, and when this one hits v1, or this thing hits a1, v1, then we get 0. Now we get 0 because v1 is an eigenvector, and it's in the null space of that matrix. So good. Now we've got 0 there. Do you see why? Because t a1 v1 minus lambda 1 a1 v1, and then the a1 pulls out, and t v1 is just lambda 1 v1. I'll just write it. So that's 0. Then the rest of them hit 0 and give 0. And very similarly, to show that p of t v3 is 0, what we'll first do is do t minus lambda 3. It'll hit v3, and because of the minus lambda 3 v3, it'll cancel off the third term here, leaving just the next two. And that means that this thing is in the span of v1, v2 only. But then we're going to hit lambda 2, or t minus lambda 2 to it, which will take this vector here, and it'll put it into the span of v1, and then we'll hit t minus lambda 1 of it, which will finally give 0, and then we'll do all the other factors, and they eat 0 and spit out 0. So that's how it goes, and so it's now clear that p of t vk is equal to 0 for all k, and we're done. So now take a look at number 9 and read it and pause the video. So if T has an upper triangular matrix in some basis where the eigenvalues on the diagonal. Prove it. Okay, so let's imagine that this is the matrix of the linear operator. Let's just even imagine it's just on a three-dimensional space, but we could keep going if we wanted. So imagine that. The claim is that these three numbers are the eigenvalues. Okay? So it's clear that v1 is an eigenvalue, but it's not clear that it's clear that lambda 1 is an eigenvalue. It's not clear that lambda 2 is an eigenvalue. So what do we have to do? So if we take t minus lambda 2, so how do we prove that lambda k, how to show that the diagonal entry lambda k is an eigenvalue? Well, show the null space of t minus lambda k times the identity is non-zero. Show that there's some non-zero vector in there, right? If we can show that, then we're done, okay? Now, remember that span of v1 through vk is an invariant subspace. So let's restrict t to that span. Let's call it u. Restrict t to that span. then the dimension of u is k, right? But by the fundamental theorem of linear maps, that's equal to the dimension of the null space of the operator. Oh, and let's not restrict t. Let's restrict t minus lambda k times the identity to u. T minus lambda k times the identity plus, this is true for any operator, so including this one, we have rank nullity, or the fundamental theorem, the dimension of the range, t minus lambda k I. Okay, so then the dimension of u, the span of v1 through vk, is k. So if we can show that this range has dimension less than k, we're done, because that means this has to have dimension greater than 0. Right, like imagine that this dimension of the range was k minus 1, then this dimension would have to be 1 so that we get k when we add up the dimensions. If this one was k minus 2, then this one would have to be 2. And as long as this thing is not 0, and the only thing that's going to go wrong is if the dimension of the range here is k, then the dimension of the null could be 0. And then we don't have an eigenvector. So we want to show that the dimension can't be 0. We'll show that the range has dimension less than or equal to k minus 1. Okay, so let's look at the range. What is the definition of the range? So the range of t minus lambda ki restricted to u is just by definition all the things that you get by applying t minus lambda ki to some vector v, or let's call it little u, such that u is in big U. What was big U? It was the span of v1 through vk. That's just the definition of the range of any operator. It's just all the outputs you get when you plug in the inputs. And here we're viewing the input space as this invariant subspace. Okay, so let's just take something in U. Any little u in U can be written as c1 v1 plus all the way up to ck vk. And let's apply t minus lambda k to it. What do we get? We get t c1 v1 plus t c2 v2 plus all the way up to t ck minus 1 vk minus 1 plus t ck vk. So I just applied t to everything over here. Now I'm going to subtract when I apply lambda k times the identity to everything here. So I'm going to get c1 lambda k v1 minus c2 lambda k v2 minus ck minus 1 lambda k vk minus 1 minus ck lambda k vk. Okay. Now, what's this? Remember, the matrix is upper triangular with diagonal entries lambda k. So this is just, well, the ck pulls out, and then the t hits the vk and gives you some number times v1 plus some number times v2 all the way up to lambda k times vk, and then everything else after that is 0. Because remember, our operator has some stuff above, but then lambda k as for lambda. So we don't care about any of these. They are there, though. But this part is going to cancel this part. And now all of these are linear combinations of v1 through vk minus 1, correct? All these. And then look here. These are all going to be linear combinations of v1, v2 up to vk minus 1 only. Okay, we're going to get that the dimension is only k minus 1 at most. And let's look at these. When t hits v1, it spits out lambda 1 v1. When t hits v2, it spits out some b1 v1 plus lambda 2 v2, which is, again, only going to go up to v2. When t hits vk minus 1, it'll only go up to k minus 1. There will be some coefficients that are non-zero before that. But the point is that it's now clear that that everything in the range, when we do t minus lambda k to some element of the space, it is going to be in the span of v1 through vk minus 1. But these are only k minus 1 vectors. So that means that this dimension is less than or equal to k minus 1, which means this dimension has to be greater than 0. It has to be at least 1. And if it's at least 1, then the null space has at least some non-zero vector. That non-zero vector will be an eigenvector. So in particular, like for this matrix here, the third basis vector v3 is not necessarily an eigenvector with eigenvalue lambda 3, but there is some vector in the span of v1, v2, v3 that is an eigenvector with eigenvalue lambda 3. So that was tricky, but we're done. Okay, read number 10. Pause the video. Okay, so T from V to V has an upper triangular matrix in some basis, right? You could say it has a basis where the matrix is upper triangular in some basis if and only if the minimal polynomial of T factors into linear factors. So this is true over R or over C. If your minimal polynomial factors into linear factors, then you have an upper triangular matrix. If you have an upper triangular matrix, then you factor into linear factors. So this is a tougher proof. I would say that you should try to understand it, but I wouldn't ask you to reproduce this entire proof on a test, for instance. It's just too much. I might try to think of a easier problem that's related, but it's just kind of too much of a ask to do this one. But you should know the result. This is the result. The minimal polynomial, if it factors into linear factors, then you get an upper triangular matrix. And I want to just give you a heads up on a future result. So like x minus 2, x minus 3, x minus 3, if that was the minimal polynomial of some operator, t, then you get an upper triangular matrix for sure. Okay? But here's the thing. You would not get a diagonalizable matrix because of these repeated factors. Okay? So if you didn't have this factor, then what we'll later prove in the book is that if your minimal polynomial is factors into linear factors where each factor is distinct, that happens if and only if you're diagonalizable. And that is a theorem that we will see soon. So the minimal polynomial really determines how simple your operator is. It determines how simple the matrix looks. If the matrix is going to be upper triangular, then your minimal polynomial factors into linear factors, if and only if. If your matrix is going to be diagonal, so everything up here is 0, all these are 0, and you only have non-zeros along the diagonal, that's the simplest possible form, then your minimal polynomial is going to factor into linear factors, but all of the factors will be distinct. So be on the lookout for that theorem. Okay. Look at number 11. Read it. So here now we require complex. Every operator on a complex vector space, finite dimensional, has an upper triangular matrix. Why is that true? Why do we need complex? Because every operator has a minimal polynomial, but over the complex numbers, every polynomial factors into linear factors. Because those are the roots. And you have, anyway, look at chapter 4. You need to know that. So over the complex numbers, your minimal polynomial, which always exists, factors into linear factors every time because you're over the complex numbers. You always have roots. And so what we just proved, well, we didn't prove it, but the book proves it. That means that we have an upper triangular matrix. So great. Over the complex numbers, every single operator, no matter how ridiculous, you can always find some basis that'll make it upper triangular. And that is nice. That means your matrix is nice and easy looking with zeros below the diagonal. Okay. And in particular, that means you always find a sequence, a nested sequence of subspaces. The span of V1 is an eigenvector. Then there's some plane where the span of V1, V2 is invariant. and contains V1. And then the span of V1, V2, V3 now is a three-dimensional subspace that contains, and so this is called a flag. I think because you take a flag and then attach a plane, and then anyway, I don't know how to draw higher dimensional things, but I don't need to draw higher dimensional things because I know linear algebra. So I can compute in higher dimensional spaces just as easily and without drawing any ridiculous pictures, even though I drew one ridiculous picture. Okay, so that's good. On to diagonalized operators next time.